This is a video on the moments of inertia and kinetic energy. The question states, find I sub x, I sub y, and I sub 0, which are the moments of inertia about the x-axis, the y-axis, and the origin, and x double bar and y double bar, which are the radii of gyration about the x and y-axes, for the lamina bounded by y equals 2 minus x, y equals x squared, and density function, rho equals k times x squared y. So first let's sketch a picture. We have y equals x squared, that's the parabola. We have y equals 2 minus x, that's the line. And we see they intersect at the points negative 2, 4, and 1, 1. I put my little man in. Notice that his feet are at the curve y equals x squared, and his head is at the line y equals 2 minus x. And the farthest left this little man can get is at negative 2 for x, and the farthest right is x equals 1. So I need the mass for x double bar and y double bar. So let's calculate that first, which is a double integral over the region x equals negative 2 to x equals 1, and y equals x squared to y equals 2 minus x, of the density function kx squared y times dy dx. And I used a calculator, which I'll use for all of these integrals. I could do it by hand. It's just a little bit tedious. And the calculator gave me that it was about 7.6 times k. Okay, there's the mass. Let's find the moment of inertia about the x-axis, which is a double integral over the same region of the distance from the x-axis, which is y squared, times the density function dy dx. So here's the moment of inertia about the x-axis. We have the double integral. We have the same bounds. And we put y squared times the density function, dy dx. And my calculator gave me that this is about 60.6 k. For the moment of inertia about the y-axis, we take the integrand as the distance from the y-axis, and that's the square of x, or x squared, times the density function, times dy dx, and I have the same limits, and I got that this was about equal to 14.9 times k. To find the moment of inertia about the origin, that's the square of the distance from the origin to the point, which is x squared plus y squared. And notice that's inside I sub y and I sub x. So I can just add these up and say that the moment of inertia about the origin is the moment of inertia about the x-axis plus the moment of inertia about the y-axis. And that's 60.6 k plus 14.9 k, and I added those up, and I got 75.5 k. And that's approximately equal to the moment of inertia about the origin. For the radii of gyration, I take x double bar, which is equal to the square root of I sub y over m. I sub y is 14.9 k, and m is 7.6 k. So when I divide, the k's cancel, and I'm left with the square root of 14.9 divided by 7.6, which is about equal to 1.4. For y double bar, the radius of gyration about the y-axis, I take I sub x over m and take its square root, and that's equal to 60.6 k divided by 7.6 k. The k's cancel, and I'm left with the square root of 60.6 over 7.6, and that's about equal to 2.8. So I found the moments of inertia about the x-axis, the y-axis, and the origin were 60.6 k, 14.9 k, and 75.5 k, and I found the radii of gyration about the x-axis and the y-axis were 1.4 and 2.8. And I'm done with the problem.